Allahu Akbar! Allahu Akbar! Allahu Akbar! Allahu Akbar! Allahu Akbar!
1991 Gulf War airlift bottlenecks. C-141s and C-5s queued on long runways. Ground crews struggling with pallets. Cut sharply to recent 2026 Udeid footage. Airmen from a 379th Expeditionary Logistic Readiness Squadron methodically loading palletized munitions, GBU-31s, GBU-38s, onto a C-17's rear ramp under desert sun. Overlay slow motion of cargo rollers moving, asterisk. Carrying what amounts to hundreds of precision-guided munitions halfway around the world sounds routine, until you run the numbers. A fully loaded C-17 Globemaster III can tip the scales at nearly 300 tons at takeoff. To get that mass airborne from a relatively short desert runway like the ones at Udeid Air Base in Qatar, the laws of physics are brutally clear. Lift must equal weight. \L equals \frac 12 rho v squared s c_L /, where rho is air density, v is velocity, s is wing area, and c_L is the lift coefficient. In hot, thin desert air, rho drops. Short runways limit v. So you need an enormous c_L, or the wings become impractically huge. For decades, this equation created an impossible barrier. Strategic airlift meant either massive runways or tiny payloads. Yet here we are in 2026, watching C-17s load up munitions in hours for rapid deployment. How did engineers break that barrier? Map of Udeid Air Base, Qatar. Satellite imagery overlays showing increased C-17s and KC-135s in early 2026. Cut to 379th LRS ground crew in action, then wide shot of C-17 taxiing. Asterisk. The driver is simple and unforgiving. Modern conflict moves at the speed of logistics. Precision air power only works if the munitions get there faster than the enemy can adapt. Udeid, the largest U.S. air facility in the Middle East, sits thousands of miles from U.S. depots. The economic and operational pressure is to surge hundreds of smart bombs and missiles directly into theater without relying on vulnerable sea convoys or forward stockpiles. That's where the C-17 becomes a backbone of global power projection. But its real story isn't the size. It's the engineering that makes this logistics feat physically possible. Asterisk animated lift equation on screen with variables lighting up. Side-by-side comparison. Conventional airliner versus heavy lift requirement. Graph of stall speed versus wing loading. CFD simulation of airflow over a generic wing at high angle of attack showing boundary layer separation. Asterisk. Let's go first principles. To fly heavy from a short field, you need high lift at low speed. Conventional wings stall around 12 to 16 degrees angle of attack because a boundary layer separates and you lose suction on the upper surface. Add a heavy payload and your stall speed climbs. Runway length required scales roughly with the square of that speed. Physics says you're stuck. Either accept tiny payloads or build runways measured in miles. For decades, that was the trade-off. The C-5 Galaxy could haul massive loads, but it needed long, prepared runways and still struggled in austere environments. Split screen. Historical YC-15 prototype test footage, modern C-17. Cut to exploded 3D model of C-17 wing and flap system. Slow motion animation of excellently blown flaps deploying with engine exhaust vectors highlighted in red. CFD overlay showing high energy flow staying attached to flap surface. Side view of engine placement forward of the wing. Asterisk. Engineers solved it with a deceptively simple idea that required exquisite integration. Powered lift via externally blown flaps. The 4 Pratt Whitney F117 PW 100 turbofans, each 40, 400 lb thrust, are mounted low and forward. When the double-slotted trailing edge flaps deploy downward, the engine exhaust is literally blown over and through them. This does two things at the molecular level. 1. It energizes a boundary layer. High-velocity exhaust keeps the airflow attached even at extreme flap angles, up to 60 to 70 degrees deflection. 2. It increases the effective camber and circulation around the entire wing, multiplying C_L dramatically. Result? The The C-17 can generate the lift needed for takeoff and landing at speeds as low as 120 knots from runways as short as 3,500 feet and only 90 feet wide, even when fully loaded. Animated cross-section showing Coandă effect on curved flap surface. Real C-17 landing footage with flap and thrust reverser deployment. Asterisk. Add leading-edge slats that droop to further delay stall. A supercritical airfoil for efficient cruise at Mach 0.74 to 0.79, and a T-tail that keeps the horizontal stabilizer out of the wing's wake. And you have an aircraft that can haul 170,900 pounds of cargo. Think 1M1 Abrams tank plus vehicles. Or pallet after pallet of GBU, 31 2,000 pounds dams, and still operate from austere fields. Inside the cargo bay, the engineering is just as clever. The floor flips between flat for vehicles and rollarized for 463L pallets. In minutes, the massive rear ramp and door system lets Loadmasters balance hundreds of munitions pallets, so the center of gravity stays inside tight limits. Because even a few inches off and the aerodynamics go from stable to uncontrollable. Interior cargo bay time-lapse of rollers activating, pallet loading animation with weight distribution graphics. Cut to in-flight thrust reverser animation, showing upward/forward deflection for steep tactical descents, up to 15,000 feet per minute. Asterisk. And for getting back out fast, the same engines have in-flight thrust reversers that create massive drag, letting the C-17 descend like a tactical fighter, while keeping the nose pointed safely away from debris on the ground. This isn't marketing. It's physics made workable through relentless systems integration. Graph comparing C-17 fuel burn per ton-mile versus commercial freighters. Cut to maintenance bay footage of flap mechanisms and engine exhaust areas. Cost overlay, asterisk. But real engineering is compromise. Those blown flaps and 4 high bypass turbofans are thirsty. Fuel consumption is significantly higher than a pure long-range airliner. The reinforced titanium flap structure that survives constant hot exhaust adds weight and maintenance hours. Unit cost? Roughly $340 million today, when you factor in inflation and upgrades. That's expensive for an airlifter. And while the C-17 is rugged, in a peer conflict its large radar cross-section and lack of stealth mean it needs fighter escort or standoff distance, another logistical multiplier. Montage of C-17s in action worldwide. Airdrop, desert ops, humanitarian relief. Final graph. Payload versus range curves. Fade to slow motion of C-17 lifting off a short runway at sunrise. Asterisk. So is this technology viable for the future? Absolutely. The C-17 remains unmatched for true rapid global response precisely because it attacks the physics problem at its root, maximizing lift at low speed without sacrificing too much cruise efficiency. Economically, it's not cheap enough to change the world for civilian logistics, but for military power projection, it delivers value that no cheaper alternative has matched in 30 years of service. Nature sets the rules: lift, drag, structural limits. Human ingenuity doesn't break them. It finds the elegant trade-offs that let a 300-ton machine land where physics once said it simply couldn't. That's the real story behind every C-17 you see loading munitions at Udeid. Thanks for watching. If you want a deep dive on the C-17 supercritical wing or how the Loadmaster solves real-time center of gravity puzzles, drop it in the comments. Subscribe, related videos, sources note for transparency, asterisk, asterisk. Production notes for editor, asterisk. Keep visuals data heavy but clean graphs, equations, and Qatar-style overlays. Use real Udeid/379 THELRS stock footage where possible. Supplement with official USAF releases. Music, subtle, low-tempo orchestral underscore. Never dramatic Hollywood. Total runtime tunable by tightening visuals. These stay strictly analytical, first principles focused, and centered on aviation/aerodynamics, while using the Udeid loading scene as the perfect real-world hook. Ready for voiceover recording.